Yesterday, we sorted letters, weighing words on a brass balance scale. Today, we leave the post office behind and climb a little higher. Welcome to the flower meadow. 3 kinds of iris grow here. Setosa, in the blue patch. Versicolor, in the lavender. Virginica, in the gold. They've grown side by side for as long as anyone remembers. But look, here on the path, a single flower, freshly fallen. No label, no patch, no name. Which family does it belong to? There is a very old, very gentle way to answer that question. You don't need a rulebook. You don't need an equation. You simply ask the flowers growing closest to it. That is the whole idea of K nearest neighbors. If this feels almost too simple, stay with me. Simple things, done carefully, can be quietly remarkable. Before we can ask the neighbors, we should meet them. Every iris in this meadow can be described with just 4 gentle measurements. The length and width of its sepals, those are the outer leaves that cradle the flower, and the length and width of its petals. 4 numbers, that's all. Setosa flowers are small and tidy. Versicolor sits comfortably in the middle. Virginica grows the longest, most generous petals. Notice something lovely here. We never need to explain why a setosa is a setosa. The measurements quietly tell the story on their own. This is one of the most famous datasets in all of machine learning. Botanists gathered it nearly a century ago. 150 flowers, 50 of each kind, and it still teaches beginners today. Let's bring it to our work table. Let's read this little card together, slowly. At the top, it says every iris carries 4 measurements. The first is sepal length, in centimeters. The second, sepal width. Then come the petals, petal length, and petal width, both in centimeters too. 4 gentle numbers, that's the whole description of a flower. And at the bottom, the 3 families we'll be meeting all episode: Setosa, Versicolor, and Virginica. Whenever you see these names later in the code, remember this card: 4 measurements in, 1 family name out. Let's open the Meadows ledger, line by line. First, the imports load iris comes straight from scikit-learn. This dataset is so beloved, it lives inside the library itself. No CSV file needed today. Watch the second line run, load iris, and there it is, 150 flowers, pressed carefully into the pages. Now we build a data frame, our tidy linen table, 4 columns of measurements, and a species number, 0, 1, or 2. Numbers are useful for computers, but names are kinder to people, so we map them. 0 becomes Setosa, 1, Versicolor, 2, Virginica, and DF head. The first 5 flowers step forward, all Setosa, all with those small, tidy petals, 1.4 centimeters long. See how the numbers agree with what we saw in the blue patch? Take a moment here. This is the quiet beginning of every project. Simply looking at what we have. Let's walk through this code, 1 line at a time. First, from scikit-learn datasets we import loadiris, and we import pandas as PD. Then we call loadiris and keep the result in a variable named iris. Next, PD data frame turns iris data into a table, using iris feature names as the column names, and we store it in DF. We add a new column called species, filled with iris target. Then we map those numbers to names. 0 becomes Setosa, 1 becomes Versicolor, and 2 becomes Virginica, all saved in a column called species name. Finally, print DF head shows the first 5 rows, all Setosa, with petals 1.4 centimeters long. Let's explore, gently. 150 flowers, 6 columns, and when we count the families, 50, 50, 50, perfectly balanced. That's rare, and it's a gift. No family will shout louder than another. Now watch what happens when we let the meadow draw its own map. We plot petal length against petal width, and look, the flowers arrange themselves. Setosa gathers in its own quiet corner, far from everyone. Versicolor and Virginica sit closer together, neighbors, with a soft, blurry edge between them. This picture is the whole episode, really. Flowers of the same family grow near each other. So if a mystery flower lands on this map, its neighborhood already knows the answer. We just have to learn how to measure near. Take this gently, line by line. First, print DF shape. It tells us 150 rows and 6 columns. Then value counts on the species name column. 50 Setosa, 50 Versicolor, 50 Virginica, and DF describe gives the means and ranges. Next we import Matplotlib Pyplot as PLT, and open a figure, 8 by 6. Now a small loop. For each name and color pair, Setosa, versicolor, Virginica, we take a subset of df where species name matches, and plt scatter draws petal length against petal width in that soft color, with alpha 0.8. We label the axes, give it the title The Meadow Zone Map, add a legend, and plt show paints the picture. Before we measure any distance, we need to be fair about it. Look at these two rulers. Sepal length runs from about 4 to 8 centimeters. Petal width barely reaches 2.5. If we measure distance with the raw numbers, the big ruler drowns out the small one. The loudest feature wins, not the most important one. KNN lives and breathes distance. So this step is not optional, it's kindness to the data. First, the split. Watch the gate. 120 flowers stay with us to learn from. 30 wait in the courtyard, unseen. They'll test us honestly later. And stratify equals y makes sure each family is fairly represented on both sides of the gate. Now the calibration frame. Standard scalar reshapes every ruler so each feature has a mean of 0, and a spread of 1. Every measurement now speaks at the same gentle volume. One quiet but important detail. We fit the scalar only on the training flowers. The test flowers receive the same rulers, but they never help build them. The courtyard stays honest, line by line. Softly, we import train test split and standard scalar. Then X takes the 4 feature columns from DF, and Y takes the species column. Now train test split divides them. Test size 0.2 keeps 30 flowers aside. Random stat 42 makes it repeatable. And stratify equals Y keeps every family balanced. We receive strain, stest, itrain, and itest. Next, we create a standard scalar named scalar. On the training flowers we call fittransform. The scalar learns the means and spreads, then rescales them into strain scaled. On the test flowers, only transform. The same rulers, never refitted. The print shows the first scaled flower. Small numbers near 0. Every feature speaking equally now. So what does near actually mean? Here are 2 real flowers from our ledger. They differ by 0.2 in sepal length, 0.5 in sepal width, and match perfectly on the petals. The first way to measure is the one your eyes already use. Stretch a ribbon straight from one flower to the other. Square each difference. Add them. Take the square root, 0.54. This is Euclidean distance. The ribbon across the grass. The second way, imagine you can't cut across the meadow. You must walk the stone paths, turning only at right angles. 0.2 this way, 0.5 that way. Total, 0.7. This is Manhattan distance, named for a city of square blocks. Notice the walk is always at least as long as the ribbon. It can never be shorter. And the third way, Minkowski, is simply a dial between the two. Turn it to 1, you get the stone paths. Turn it to 2, you get the ribbon. Scikit-learn's default is the ribbon, Euclidean, and that's what we'll use today. 4 measurements means our ribbon actually stretches through 4 dimensions. We can't picture that, but the arithmetic doesn't mind at all. The formula works the same. Quietly, let's follow the numbers. We import NumPy as NP, then Flowera holds 5.1, 3.5, 1.4, and 0.2, and Flowera holds 4.9, 3.0, 1.4, and 0.2. For Euclidean, we subtract Flowera minus Flowerd, square each difference, add them together with NP sum, and take NP sqrt of the total, the straight ribbon. For Manhattan, we take NP adds of the same differences, and simply add them up with NP sum, the stone paths. The 2 print lines show the answers to 2 decimal places. Euclidean, 0.54. Manhattan, 0.70. The walk is longer than the ribbon, just as we expected. Now, the training. Take a breath, because this will be over faster than you expect. In every episode so far, fit meant work, a ribbon slowly settling, coefficients nudged, thousands of times, trees growing branch by branch. Watch what KNN does instead. Fit, and that's it. The meadow simply remembers. Every flower, every measurement, pressed into a memory book. No equation was solved. No boundary was drawn. Nothing was built at all. This is called lazy learning, and it isn't an insult. It's a strategy. Most models do their thinking during training, so predictions are instant. KNN does the opposite. It postpones all of its thinking until the moment you actually ask a question. Remember now, think later, which means the interesting part, the real work. happens at prediction time. And that's exactly where we're going next. The mystery flower is still waiting on the path. Only a few quiet lines here. First, from sklearn neighbors we import KNeighbors classifier. Then we create the model, KNeighbors classifier, with neighbors set to 5, and store it in a variable named KNN. 5 means every future question will be answered by the 5 closest flowers. Next comes KNN fit, with strain scaled and itrain. And this is the entire training step. No loops, no long wait. The model simply keeps the 120 scaled flowers and their labels in memory. The final print tells us the memory book is ready. And truly, that is all fit ever did. This is the moment the whole episode has been walking toward. Let's watch the meadow think. Step by step, the mystery flower takes its place on the map. Its 4 measurements put it here, near the lavender drift, close to the golden edge. Now, watch. A circle of soft light spreads out from it, like a ripple on still water. The question it carries is simple. Who is closest to me? There. The first flower lights up. A versicolor. Distance. 0.3. The nearest neighbor of all. The ripple widens. A second flower. Versicolor again. 0.4. Third. Versicolor. At 0.5. Fourth. Versicolor. 0.6. 4 lavender voices now, each a little farther than the last. And the fifth. The ring stretches to 0.8, and it touches a virginica, a golden voice, from just across the boundary. 5 neighbors found. K equals 5. So we stop. The light goes no farther. Now they vote. 1 petal each. No flower's voice counts more than another's. Versicolor. 1, 2, 3, 4. Virginica. 1. 4 to 1. The meadow has decided. Versicolor. And notice, the meadow isn't just certain, it's honestly certain. 4 votes out of 5. A confidence of 0.8. That one golden vote is the meadow gently admitting. This flower grows near an edge. That's everything. No equations were solved just now. Only distances. And a small, fair election. If it felt simple, that's because it truly is. Read this little card with me. At the top, the mystery flower. Sepal 6.1 by 2.8 centimeters. Petal 4.7 by 1.2. Then the rings. Ring 1 finds neighbor 1. A versicolor at distance 0.3. And neighbor 2. Versicolor. At 0.4. Ring 2 brings neighbor 3. Versicolor. 0.5. And neighbor 4. Versicolor. 0.6. Ring 3 reaches neighbor 5. A virginica. At 0.8. Then the vote. 4 dots for versicolor. 1 for virginica. So the answer is versicolor. With confidence 4 out of 5. 0.8. Now let's do encode what we just watched in light. Line 1. The mystery flower's 4 measurements. Exactly as we found it on the path. Line 2 matters more than it looks. Scalar transform. The new flower must be measured with the same calibrated rulers as everyone else. If we forgot this line, we'd be comparing a scaled meadow to an unscaled flower, and every distance would be wrong. It's the single most common KNN mistake, and now you'll never make it. Line 3 predict. Behind this one quiet word, everything we watched happens again. The distances, the 5 neighbors, the vote, and predict proba shows us the ballots themselves. 0 for Setosa, 0.8 for versicolor, 0.2 for virginica, 4 votes and 1, written as fractions. Versicolor. The flower has its name, and Kiko knows exactly where it belongs. 1 line at a time. First, Mysteriflower holds the 4 measurements inside a double-bracketed list. 6.1, 2.8, 4.7, and 1.2. Second, Scalar Transform passes it through the same calibration frame, giving us Mysteriscaled. Never skip this line. Third, KNN Predict on Mysteriscaled asks the 5 nearest neighbors and returns the winning class, while KNN Predict Proba returns the vote fractions. Then 2 prints, Iris target names, with the first element of prediction, turns the number into a name, versicolor, and the probabilities read 0, 0.8, 0.2, 4 votes for versicolor, 1 for virginica, written as gentle fractions. We chose 5 neighbors. But, why 5? Why not 1? Why not 25? Look at these 3 paintings of the very same meadow. With K equals 1, each flower listens only to its single closest neighbor. The boundary trembles. It wriggles around every stray blossom, drawing tiny islands around flukes and accidents. This map has memorized the meadow instead of learning it. 1 odd flower, and the whole neighborhood is mislabeled. We've met this before. It's overfitting. With k equals 25, the opposite. Each flower asks a huge crowd, and the crowd's answer washes over everything. The gentle border between versicolor and virginica disappears entirely. The map is too smooth, too general, underfitting. And k equals 5. Just right. Smooth enough to forgive one strange flower. Attentive enough to honor a real boundary. But we don't have to guess. We can simply ask. Watch the loop run. For every k from 1 to 25, we fit, we score, we note the accuracy. Each marble is one honest measurement. The curve rises, settles, and gently declines. And the pin marks our answer. One small habit worth keeping. Prefer an odd k, so the vote can never end in a tie. Let's follow the loop. We import NumPy and Matplotlib values as a range from 1 to 25, and accuracies begins as an empty list. Inside the loop, for each k, we build a k-neighbors classifier with neighbors equal to k, fitted on strain scaled and itrain. Then model score, ons test scaled and itest, appends one accuracy to the list. After the loop, plt plot draws values against accuracies with little circle markers. We label the axes, title it choosing k, add a soft grid, and show it. Finally, np-argmax finds the highest accuracy. Values gives us best, and the print announces our answer. Now for honesty, the 30 flowers behind the gate, the ones our memory book has never seen. One by one, they come forward. For each, the rings ripple. 5 neighbors vote. A tag is tied. And then we open their true names. 29 out of 30 correct. About 97%. Look at the planting bed. All 10 cetaceous. Perfect. That quiet corner of the map keeps them safe. All 10 versicolors. Right. And virginica. 9 of 10. One virginica, growing close to the lavender border, was gently mistaken for a versicolor. That's not a failure to hide. It's the map telling the truth. Where families overlap, neighbors can mislead. Even the best gardeners posit that border. The report reads the same story in numbers precision. Recall. F1. All high. All honest. Our little memory book has done beautifully. Gently now, line by line. From Sklern metrics we import accuracy score, confusion matri, and classification report. Then KNN predict runs on test scaled, giving IPERT, one guessed name for each of the 30 unseen flowers. The first print compares itest with IPERT using accuracy score, 0.966, about 97%. The confusion matri print shows the planting bed, 10 setosa, perfect 10 versicolor, perfect and for virginica, 9 right, with 1 slipping into the versicolor column. Last, classification report, with target names from iris, unrolls precision, recall, and F1 for each species, perfect ones for setosa, and 0.95 for versicolor and virginica. Time to press our field guide. 2 dumps, not 1, and this matters. The model remembers the flowers. The scaler remembers the rulers. Save the model without its scaler, and tomorrow's measurements won't line up with today's memory. They belong together, like a guidebook and its magnifying glass, wrapped in cream paper, tied with ribbon, and onto the shelf it goes, beside the compass, the loom, the seed pouch, and whenever anyone finds a flower on any path, anywhere, 2 loads, 1 transform, 1 predict, the meadow will answer. A few closing lines. We import joblib, then 2 dumps. Joblib dump saves KNN into a file called iriscnmodel.pkl, and joblib dump saves scalar into iriscolor.pkl. Model and rulers, kept together. Later, in any other garden, 2 loads bring them back. Joblib load gives us loaded middle, and joblib load gives us loaded scalar. Then a sample, loaded scalar transform, on 6.1, 2.8, 4.7, 1.2. The same calibration first, always, and the print, iris target names, with loaded middle predict on the sample, answers versicolor, just as before, save together, load together, and the meadow keeps its promise. This little idea, ask your nearest neighbors, lives all around you. When a bookshop, or a music app, says people like you also loved this, that's a neighborhood vote. When a clinic compares a new patient to the most similar past cases, to help a doctor think, neighbors again. When smudged handwriting is read by matching it against known samples, neighbors. And sometimes, the most interesting flower is the one with no close neighbors at all, far from every patch. Fraud detection, and quality control. Watch for exactly those lonely points. Simple, honest, and everywhere. That's KNN. Let's read the notice board together. First line recommendations. People similar to you also loved this. A neighborhood vote. In a bookshop or a music app. Second, medical support. A new case laid gently beside its most similar past cases, to help a doctor think. Third, pattern matching. Handwriting, images, fingerprints, each one recognized by finding its nearest known samples. And fourth, anomaly detection. A point with no close neighbors at all, far from every group, is worth a gentle look. Fraud detection and quality control watch for exactly that. 4 quiet places. One simple idea. Ask the neighbors. Every flower in our meadow had a name. Setosa, Versicolor, Virginica. Our only task was to match a stranger to a family that already existed. But listen, beyond that gate, there's a morning market. Shoppers filling the square, and not one of them wears a label. No names, no groups, no answers written anywhere. What if the data has no names at all, and the groups themselves are what we must discover? That is a different kind of learning, and it's wonderful. Rest here a moment. When you're ready, the next door is open. One small card to close the day. The first line simply says, "Next time." Beneath it, the name of our next adventure. Episode 11. KMeans clustering. Notice that the K appears again, but this time it will mean something new. Not the number of neighbors we ask, but the number of groups we must discover. And the last line names the place we're going. The Morning Market Square. A busy little square where nothing wears a label. Read the card once more, softly. Episode 11. KMeans clustering. The Morning Market Square. When you're ready, that's where we'll meet. You classified a mystery flower today, with nothing but distance, and a small fair vote. Sleep well, little meadow. We'll see you at the market.